Okay, so here we go. We have triangle RST, that's the big triangle, and we have two parallel sides. We have the segment in the middle of the big triangle that's parallel to the base of the triangle. And I call it the base only because it's on the bottom. We want to prove that RP is over PT is equal to SQ over QT. So what I'm going to do is I'm going to take these two triangles. I'm going to take PTQ, PTQ. I'm just going to sketch it, PTQ. And then I'm going to sketch the other triangle. There we go. It doesn't have to be perfect. So we've got PQT, RST. And if I were to take this triangle, let's see how close I got it. Let's see how close I got it. Oh, pretty close, almost. That's actually not bad. Okay, so all I did was I took the two triangles and boom, voila, I separated them. Well, what do we know about these two triangles? We know that PQ is parallel to RS, and that's because it was given. So I'm gonna use a pen here because that's gonna show up better on this picture. That was given. So that was given information. Angle 1 is going to be congruent to angle 2. Angle 1 is congruent to angle 2. And angle 3 is congruent to angle 4 because when you've got the parallel lines cut by a transversal, so here's my transversal, parallel lines cut by a transversal, we've got corresponding angles are congruent. So I'm going to write that down. If parallel lines, then corresponding angles are congruent. And I'm going to mark this picture right here. This was angle 1, right? That's angle 1. This is angle 2. And then this is angle 3, angle PQT. That's angle 3. And angle RST is angle 4. So now this green triangle, triangle PQT, is similar to triangle RST, the bigger purple triangle. Those two triangles are now similar by angle-angle similarity. So by angle-angle similarity postulate. And now we can say that because the two triangles are similar, because the triangles are similar, we've got RT over PT. Those two sides correspond. RT, here's RT, and here's PT. Those two sides correspond. That ratio is equal to ST, right? Here's ST over QT. So we're writing these ratios with the triangle on the right over the triangle on the left. Right over left, right over left. And that's going to equal, yeah, the bottom part. I'm not sure that that matters because we just need to prove RP. We're talking about these sides. We need to prove that RP over PT is equal to SQ over QT. So we don't really need to worry about those bases. So I'm not even gonna go there. I'm gonna take my eraser mark and I'm not gonna continue to write the rest of it. Now what allows us to say that RT over PT is equal to ST over QT? Well, because the triangles are similar. So corresponding sides of triangles, similar triangles, are in proportion. So they already had the answer for us. So this part right here is this right here. Okay. Yeah, that's kind of all messed up. This is better. There. I don't know what kind of shape that was. It was definitely what? Concave. Number 5. RT is equal to RP plus PT. So what I'm going to do right here is I'm going to look right here. So that right there, RP plus PT. RP plus PT is the whole thing. So a part plus a part is the whole thing. That right there is your segment addition postulate. And ST is going to be true on the other side. SQ plus QT is equal to ST. So that right there is our what? Segment. I better write this in black so we can see it. Yep. Segment addition postulate. That's from a long time ago, right? Seems like forever ago now. Then we're going to break it up and we're going to say, RP plus PT over PT is equal to SQ plus QT over QT. What allows us to say that? What allows us to say that? RP plus PT. RP plus PT. Where did that come from? RP, well, I'm not going to cross it out. RP, let's use green, plus PT over PT. Oh, look at that. Over PT. So this right here, isn't that the same as that one? RT over PT. And in place of RT, we're putting RP plus PT. So look at that. We're substituting that in. It's very nice. And then SQ plus QT over QT. Well, SQ, we just substituted that in right there, right? So this right here is called substitution. So by property of substitution, we, voila, created this other looking form of a proportion. And now we're able to say, whoa, RP over PT is equal to SQ over QT. That is a property of proportions. That is a property of proportions. And look at this. It tells you where to look, page 245. Just a hint, those property of proportions, you know how much I loved them. When I showed you about property of proportions, I absolutely love proportions. They're how they really make the world go round. So if they're that important, and I love them that much, you need to make sure that you know them, because that's very, very likely that you will see them again on a high stakes exam. Okay, so there's our proof that shows when you've got those similar triangles. So when you've got that situation happening, we've got this proportional length situation that is indeed true. It's called the triangle proportionality theorem. And what that says is, if a line is parallel, if a line parallel to one side of a triangle intersects the other two sides. So that was that right there. If a line parallel to one of the sides of the triangle and intersects the other two sides, then it divides those sides proportionally. It divides those sides proportionally. So that'll give us some opportunities to do some pretty cool math. So I'm going to show you some different proportions we can set up with this triangle that fits the triangle proportionality theorem. The triangle proportionality theorem. So in the next video, we'll create some of those proportions here